get all the physics grad students together for a group photo.
I'm a chemistry graduate student. Are you sure?
Oh, are you a grad student? Or?
Yeah, but I'm not a physics graduate student. I'm
Oh.
chemistry.
Oh, okay. Well, if you want to be a part of it, you can. But we're no physics.
Okay.
The day that works for everyone so far is next Friday, November 18th, from 1 to 3 p.m. I don't know the certain time yet. I'm still trying to talk to everybody.
Okay.
But-
Or do you mind I ask your email or kind of thing?
Yeah. Here, I'll write one now.
Thank you.
See? I can read that. I got that one already. JHH 01.
Okay.
That little
Okay.
Just send me an email, and then once I find a time, I can send an email out.
Okay.
Great.
Thank you.
Uh-huh. You guys hear about that? Are you guys free on Fridays?
This Friday, tomorrow,
Well, next
next
Friday.
Friday.
From 1 to 3 p.m.
1 to 3 p.m. we have program.
Oh, no, I'm trying to do something. Yeah, I'm trying to get a group picture.
Oh, yeah, sure.
Do you have a meeting next weekend, Rishi? Not next weekend, next Friday.
Next Friday.
Yeah, from 1 to
No.
3.
We don't have, but we can.
I think.
I don't think you have any more meetings. do you?
Yeah,
Did
we
you-
have finished
Yeah.
in the next week.
All right,
yeah.
cool.
Yeah.
I'm trying to get a group picture,
Yeah.
just like that one.
Okay.
With like all the physics students.
And you
And
take my single picture as well.
Yeah. I'll have Dr.
Full picture.
Oh no, I'll have Dr. Goodley take it. I'll have Dr. Goodley take it.
Yes.
If we had a second semester, how much of the book would we have covered?
This,
If we had a second semester.
if we have second, actually, chapter 10. Let me see, chapter 10 definitely will go. Then maybe the chapter, let me see, chapter 10. I'm thinking like chapter 4, 5, 6, and 7, which we have not covered. These are more details about this application for Lagrange equation and for different system. Well, I don't think we can cover all, even second semester. Yeah. This actually now, yeah, let's continue. Let me just remind you, we did the F1 type, F2 type, F3 type last time, to finish this, right? Now for F4 type, I remember at the end of class, I gave some idea, and it's transfer from the F2 and transfer F2 to F4, because F2, F4 they have keep the capital PG same, but only the change lower QG and PG. So by that way, and then we define the geometric function, then you're going to use substitute into the transformation equation, right? First calculate this one, and then go to here, substitute this one. Now, T minus H, now, J plus K plus E and T, right? Plus substitute this, then we find this. So I just want to save time since we have a lot. At least I need to finish chapter 9, otherwise chapter 9 and because chapter 9 only discuss the canonical transformation, and the goal, remember our goal is transfer, make this QJ, PJ to the new one, such that this is a cyclic, right? But for chapter 9, just tell us how to transfer. Then chapter 10 will give us this cyclic kind of the measure. So let's see how much we can go. But at least I want to finish chapter 9 for the most important part. So now today, let's do some of the examples. Since we discussed the transformation, then we are going to know how to make the transformation, right? So now, do some examples. First one, let's consider the F1 type. F1 type is the geometric function is a function mixture of the old general coordinates and new general coordinates. So example, very simple one is F1, just the products of old general coordinates and new general coordinates, right? So if we do this, and yes, it is one of the trivial sample, right? Very simple case, but it satisfies the condition here. So now let's do that. Suppose we select this. Then we are going to find what's the transformation, right? Between old and new, right? So this, because, see this partial derivative gave us the relation between old and new one, right? So old PG is partial F1, partial PG, right? Then here F1 is this, so that is capital PG, capital QG, right? And then the capital PG, by that partial derivative, we know that F1 type is with the partial F1 with QG, capital QG. And then capital QG gives us normal QG. So what does mean? So this means, so we have the old one transferred to the new one, just interchange, right? And this I think I have a negative somewhere. There's a negative PG. So that is interchange. That means if we design or construct the F1 function is like this, then this is simply just interchange. The Qj become my negative Pj, and Pj become Qj. Right? That is interchange. So that is the role played by this type of F1. So if that case, then let's so this is give us from here we have the transformation equation, right? This is between old and new and old. Then we can do the Hamiltonian. So now we are going to second one. We are going to find the new Hamiltonian, right? K capital Qj and capital Pj time according to I didn't. But if you remember, all the after we introduce these types, all this the new Hamiltonian is the old Hamiltonian plus partial derivative of Fi and 1, 2, 3, 4, right? All of 6, remember. So then what that means, once we have the geometry function, we have the transformation equation, then we are going to substitute into this Hamiltonian, so we can get the new Hamiltonian. So now let's see here, we already have, right? So new this is equal to h Qj, which is a function of capital Qj, capital Pj t, and lower Pj, which is also a function of capital Qj, capital Pj t, and plus partial f1, partial t, right? So now, see, f1 does not depend on time explicitly, so this term, it disappeared. So that's equal to h, right? So new one, old one the same, but the formula is different, right? So now let's, so now here, okay, this one, if whatever the Hamiltonian, the old one is, now the old general coordinates is equal to here, negative. So that means I'm going to replace the negative, capital Pj. And the old Pj is new capital Qj, and also does not, okay, maybe we can have. So we immediately got this. That means you can simply just replace the old Hamiltonian by replace the old Qj, Pj by this. Then you got the new one. That is the Hamiltonian in terms of new general coordinates, or new canonical variables. Then let's double check. Right? So if we say that, if we make this transformation, that's be canonical. If canonical means the Qj dot, so now let's check. Check. If Qj dot equal to partial K, partial Pj, that is we are going to double check, because that's make sure that's be equal, right? If this canonical is be equal, so now let's double check. Okay. So now let's see, because capital Qj, right, dot, since capital Qj is equal to the lower Pj, right? So that's equal to lower Pj dot, right? By this transformation equation. And lower Pj dot follow the canonical, because this lower and old canonical variables are the Hamiltonian follow this Hamilton's diffusion motion. So that's be negative partial h, partial Qj, right? Okay, then now, let's see, partial. Now I'm going to replace Qj by this. So that is partial Hamiltonian here minus capital Pj, Qj, right? Maybe time, so you have to keep time also here. And partial negative Pj, right? So you can see here, oh sorry, I forgot negative here. Because this is negative here, right? So this is negative here. So you see this negative to cancel, so that gave us, because this one is K, right? That is, so yes. And the second one, let's look at capital Pj dot. Capital Pj dot is equal to capital, capital lower. Okay, I think, oh yeah, that's negative. Yeah, that's actually correct. So now this Pj is negative Qj dot, right? Here, this is negative. Then we go to next case. QJ dot is partial H, partial PJ, right? Then we type partial H now, negative. If I replace QJ, PJ with new one, that is this formula, and the denominator P is QJ, right? Is this one. Then you can see the numerator is K, and denominator capital Q, yes. That is this one. So yes, so you see this is very simple, but it is indeed convert the old kinetic variable to the new kinetic variable. And the new kinetic variable will follow this Hamilton's equation motion. Okay. Let me do one more, and the remaining I think you can do yourself. The second one, F2 type. Okay, F2 type, for example, F2 just here, F2 is a function of Q, old QJ and capital PJ, right? So this simply summation QJ. That is a very simple case. And then with this, so now let's see. Okay, let's look this one. That is F2 type and give us a partial derivative. From here we can get this transformation equation, right? The relation between old and the new kinetic variable. So the first one is P, right? Pj is equal to partial F2, partial Qj, and then here, partial Qj, so that is capital Pj, right? Then this second one, capital Qj, is partial F2, partial capital Qj, which is capital. So what that means, identical. No transfer, right? Old and new are same. So if this same, that means here, old, old and new here, same. Old Q and old P is also new P. That is by this transfer. So F2 type is follow this. Okay. So if identical, then you can double check the others. That's K, capital QJ, capital PJ, T is equal to H, QJ, PJ, T, right? Partial F2, partial T, so that is again 0. So that means they're equal to this. Okay, and then now let's double check. I think I will do one more, and then the remaining part I will do that. So now let's look at capital QJ dot. It's not about capital lower QJ dot, right? Because they're equal. That is partial H, partial PJ. Since partial PJ, H equal to K, right? They are equal. Since this is equal to 0, P is capital B. Yes, right? And then the PJ dot is lower PJ dot since they are equal. And negative partial H, partial QJ. Then the negative partial H is K, QJ is capital QJ. Yes. So you see F1 type, if we set up that one is interchange. If F2 type is just identical, and if it's a little complicated, it is basically keep this identical. So now let's consider F3 type. F3 type, okay, sorry, this is wrong, right? So now I'm going to get F3 here. F3 is Q, P and Q, right? P, lower PJ and Q. So now you replace this one guy. Then we follow this, right? This lower QJ, here is this PJ is QJ. 3, this is the P. Okay, here, so that gives this one, right? Then another one is capital PJ, right? Capital PJ. capital PJ, right, is, here we have a negative. So this one is also negative. And then we have this, so we have a negative PJ. So what that means? PJ, they are negative, and the QJ, they are also negative, but identical since no change, only by negative sign. So this one is identical. And do the same thing so here, like 3, and here you have minus capital QJ, minus capital PJ. So what we have to do in this case, if we set up the F3 function like this, we just simply substitute the Hamiltonian, the old canonical variables with new one but negative sign. Then you can do the same thing. So, for example, here, just be negative, PJ dot, and negative, yeah, so negative, so PJ. And then here, I guess this part, I think, very similar, so that is negative partial k, partial minus capital PJ, right? So that is partial k, partial capital PJ, yes. Second one is, you have a question? Okay. Second one is this capital PJ dot is because capital PJ is negative, negative or lower PJ. So we have a negative, 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 and negative all different class, right? So that is partial k, partial PJ, lower PJ is negative sorry, this is not P, this is P, Q, right? And then here, lower QJ is partial k, that's direct, minus capital this, partial k, partial yes. And leave F4 for yourself. Do your F4 tab. Okay. Example is F4 is also simply the product of because it's a function of lower PJ, capital PJ, and we are going to use this. So then because the QJ is partial F4, partial PJ, so that is capital PJ, and capital KJ is partial F4. It's a negative sign. Okay. Partial capital PJ, so that is lower PJ. So we have QJ is negative capital PJ and PJ is capital PJ. So that this is an interchange, right? Q to P, P to Q, but Q to P is another sign. Then you, this part I want you to do yourself. You can double check. Yes, it is canonical variables, And this transformation, indeed, it is canonical transformation since it gave us this, follow this Hamilton separation motion. Now, more complicated. This is a simple, just select one type, one of the type, right? 1, 4, 2, 3, 4. But how about the mixture? So now let's do example is if we have a mixture of the geometry function, mixture of this one of two of the type. So this number 5. Mix. Mixed 4. Okay. Mixture 4 example. Okay. Let's select. We consider two. 2D system. 2D system we have a Q1, Q2, P1, P2, right? That is in the old canonical graph we have two particles. Each particle has its general coordinates and its conjugate coordinate. So now let's consider 2D system. Now we set up the genetic function is like this. It's mixture of F1. Let me give you this. What does this? F1 here, right? F1 is a mixture of the old canonical variable and new canonical variable, but this only for particle 2, right? And F2 is for particle 1, Q1 and P1. So F2 here, right? Q and P. So now, what happened? Effect. Okay. So that is general, right? Then if we F2, you see, this is a function, the general function, you see here, if F1 is only equal to F1. But if F2, we have to add this term, right? So here you have minus, that one is a capital Q2, capital Q2, right? Sorry, what? This one. So that is F2 type, which includes under F1 type. This is a mixture of these two types. For that, I mean, we want to, if F1 type, as we say, is interchange, so we want to interchange the first particle, the Q1, P1, with a new capital Q1, P1. And the second particle, the second particle is interchange. But first particle is still identical transfer. That is the way, the idea. Okay. So in this case, now let's see what this is. We have the solution, right? We already did it. So now we are going to, for the new one, we are going to derive the relation something like this, right? So if this, then what you need to do is first total time derivative, because we are going to sub this one into the canonical equation of canonical transformation. So look the total time derivative of this new function, the mixture of this. That's be partial f. Okay, so if you see this function is Q1, Q2, capital Q1, capital Q2, and capital Q1, right? That is this function. You see we have a Q2, Q2, Q1, capital P1, capital Q1. So that is function this. So when you do the derivative, you have to consider all these terms, right? So we have 5 terms now. The first one is now, I think I need to explain this because later you follow that. So now, first one should be, I look this one, right? So F2, partial derivative and partial, second one and capital, this one too. But the order you can do this first. You said this is number 1 and number 2. It's up to you. I just follow this the position here. So now this one finished, and now of this F Q1 dot plus partial F partial capital P1 dot, right? Okay. Then we have this term. So so now minus Q1 dot capital P1 minus Q1 capital P1 dot, right? That is the total time deleted on this term. And you know now, so then you know this only f1 has a function q2. So here, that's equal to partial f1, right? q2. And plus second one also only the f1 has a factor q2. Partial f1. Partial factor q2. Now, then the q1 is only f2, so then it actually is equal to partial f2 only. q1, q1 dot, partial f2, only partial factor p1 dot. And the remaining is 2 will keep it. Okay, this is the total. Then we are going to substitute it here. This is the initial, right? This is a this one is for this each individual. But now if we have mixture, we have start from original. Remember original? Is this formula, right? That is the equation of the transformation. Any transformation follow this, right? So when you deal with any transformation, the generating function you first found it, then you are going to substitute with the total time derivative. Then you are going to see in this case what is the final result, where what is the relation from the partial derivative, and then what is the final relation between k and h. Okay. Let's do this. So I think I don't need to repeat, but we can look here, right, on the page column. See, left hand side, we have a qt dot. And then, okay, here, because, yeah, this is a general function, right, so now, because we have only two particles, so now here we just extend it. Use q1 dot p1 not plus q2 dot p2 minus h, right, equal to capital Q1 dot capital P1 plus capital Q2 dot capital P2 minus K plus df dt, right? Okay. So now we are going to compare both sides to be the coefficient for this Qj dot or Pj dot is equal. So now we can see here, this is a Q1 dot, and from here, we have Q1 dot here, right? So for Q1 dot, with the Q1 dot, we have P1 equal to partial F, but then partial F of Q1 is partial F2. So that is partial F2, partial Q1. Yes, partial F2, partial P1. Okay, that is for, so then we put, how about this a Q2 dot? This is a Q2 dot. We have a Q2 dot, here we have Q2 dot. So the Q2 dot in this case is P2, right? P2 equal to partial F, partial F1, right? Partial Q2. This is for Q2 dot. Okay. Now, left hand side here, we finish, right? So the remaining part is right hand side. The right hand side, if we let's look at capital Q1 dot. Capital Q1 dot is this one, right? We have this one. Then they are we cancel each other. So capital Q1 dot, that gave us capital Q1 dot. We have a P1 be equal to P1. That is nothing give us new, right? Because this is P1. Negative P1 and this P1, so they cancel actually. So let me just, since this does, okay, let me just do this. I'm going to, so this one cancel, right? Now let's see, capital Q2 dot is this one. We have some other cancel term. Okay, we do not have, so only that term cancel. So now we're going to see for capital Q2 dot. Capital Q2 dot is capital P2, right? This one equal to negative, right? Because they are in the same sign, so negative partial F. Partial F what, right? Okay, so this one we finished. Then now, so that part we finished. Now we come to here. You see, we have finished this one. We finished. Q2 we finished. Q1 we finished. So only this term, right? Capital P1 dot, and this one capital P1 dot. So last one is, which is here the Q1 equal to partial F2. This is F2, right? Okay. So we open this. And then when we have this, then you can see here all the terms cancel, right? So then you get the left side is negative Hamiltonian equal to negative, and then you pass partial T, right? The other term are cancelled. So E partial F partial T is 0, then K equal to H. Then what you need to do is let me just do this. So here K is capital Q1, capital Q2, capital P1, capital Q2, and H Q1. There's the Q1. Q1 still. Oh, okay. I didn't get, so I'm not just right now here. Q1, Q2, P1, P1. I didn't give the detail about F1, F2, so we do not know. We just know the relation here. And just practice, right? Please. I want you do yourself if F1 is just a simple product of, is a simple product of Q2, capital Q2, and F2 equal to a simple product of Q1 and Q1. Okay. Check capital Q. Check this. We may have the details so you can check whether it is satisfied. So one more, and it's a little more general. So now let us consider another mixture, which is again it's still 2D. Okay. This is F1, F2 type, right? Like this F3, F2 and F3 type. Can I erase this now? Okay, you talk. Can I erase this now?
Yeah.
Okay. So suppose we have f1 is a function of q1, p1, p2. Let me ask you, which kind of a mixture here? Look, the first particle is mixture of Q1, P1. So which one? This one, right? And this is Q2. The second one P and Q is this one. So that is F. This is a F2 is actually right. So that is another type of mixture. But here I didn't give any function. Just let you know this type of. Then you are going to what you got to do is first. Okay. This is F prime. If F prime and then remember F. Okay. If F2 we have not this term, be careful. The total the generating function when you select 2 you need at this term. We select 3, so we have another 2 terms. So F should be F1, Q1, P1, P2, Q2, P minus. This is the first one is capital Q1, capital P1, right? F2, because F2 is what number 1. Then plus, so this plus is lower Q2. Okay. So then we need to the total time difficult here to P is partial F1, partial Q1, Q1 dot, partial F1, partial Q2, Q2, no, okay, no Q2, right? Here, no Q2, so that have no P1, right? P1 dot. All the 4 particles right here. Partial F1, partial Q2, Q2 dot, partial F1, partial capital Q2, capital Q2 dot. Then the remaining is 4 terms, not okay, so then capital Q1 dot, capital P1 minus capital Q1, capital P1 dot, and plus Q2 dot, Q2 plus Q2, Q2 dot. Those are the total time derivative of generating function. Let's sum this into, since we have only 2 particles, this is Q1 dot, P1 plus Q2 dot, Q2 minus H equal to capital Q1 dot, capital P1 plus capital Q2 dot, Q2 minus K plus okay. So do the same thing. Now let me give you the result and I want you to double check yourself if it is correct. So finally we found P1 is equal to partial F1, partial Q1, and capital P2 is partial F1, partial capital Q2, then capital Q1 is partial F1, partial capital P1, and the lower Q2 is partial F1, partial P2. Since the F prime is only these 4 variables, so then this gave us the relation between this and the remaining part. Q1, how to transfer, and Q1, Q2, right, and then we have this is lower, so that is lower P2, this is lower P1, right? Lower P2. So the another 2 actually like flexible or unchanged, since here do not give any restriction about this. So this is a arbitrary It's really not serious if you set up this. Then you can check yourself. K equal to H equal to what? The relation between K and H. Do the same thing like substitute. When you cancel those, then you find this part and this part and some other term will be this. So then you are going to check with this. Speed power, right? Okay, so this is a really general, give you the idea. Now let us play one example and see how it works for this energy transformation. Okay, one-dimensional simple harmonic oscillator. This one, since only one dimension, it does not give us too much, but at least give us some idea what will happen if we make the canonical transformation. Okay. So that is example 5 now, example 6. 1D. Okay. Hamiltonian. Now I immediately write down here chapter 8 how to transfer from Lagrange to the Hamiltonian. We need first write down the total kinetic energy, potential energy, right? And make this transfer. That is chapter 8. Your homework will to do that. Now chapter 9 assume you already transfer, right? So now the Hamiltonian in this case they give you is a function of Q and P, since only one particle does not need the index here, which is kinetic energy part, potential energy. Suppose this the K is the constant of this the string constant. So that is Hamiltonian. Now you can see here Q is not, right? Simply. In this case, right? So yes, let's just not. But then we still can solve. This since there's only one dimension is easier. Let's see what happens. Just so the let's solve the Hamilton's equation of motion. For this system, Q dot is partial H, partial P, right? And P dot is negative partial H, partial P. Here. Okay. So then we can see here, partial H, partial P, we have P over M, right? This. Partial H, partial P, that is the Q dot. Then the P dot is negative partial Q, so we have K Q, right? So we have the, let's say, equation 1 and equation 2. Then we say do this continuity again, equation 1, and that equal to P dot M, right? Then substitute this one. So this is equation 3 here. Then there's a 2 to 3. And we have Q double dot is, since P dot is here, is negative K Q over M. And this solution simple, so but we just use this simple to solve that. Solve this, show this canonical transformation presented. So from here we know Q double dot okay, here. So this solution is very simple. we know this simple harmonic. Right? Q is magnitude or amplitude cosine omega t. Omega is the coefficient k over F, right? This is the lesson. So that is the result. Yes, because this case it is not complicated, so we can solve. But as I said here, in this case, if we write down the Hamiltonian in select this set of canonical variables, Q is not cyclic. So now, if we want to make the canonical transformation, go. Now I'm going to just CT means canonical transformation. Right? Canonical transformation, okay, I'll do this. So is we want to transform through the canonical transformation to the new capital P, capital Q, and such that Q is cyclic. Right? Then make this equation of motion for this. The Hamiltonian equation of motion is become simple. So now that is our goal. The question is how to construct Geometry function, right? With either f1, f2, or mixture, whatever. So we need to find the Geometry function or construct the Geometry function such that we make this canonical transformation, and in the new canonical variables, the Hamiltonian does not depend on Q. That is our goal. How to do that? Okay. Think about which type is suitable for us. Let's look. So you see here, after the transformation in the Hamiltonian, that general coordinate disappears, it is cyclic. So this change, this transformation will not be F2 type, because if F2 type usually is identical, right? So F1 type is possible with the interchange. So you think about it, I'm going to select F1, not F2 or 3 type. Right? F2, F3 type in general is just identical, F1 or F4. So that is the first idea you are going to consider. Okay. F1 type, which is interchange. That is element. Still, we do not know the F1 type, what kind of formula. That is depend on the experience. So here, we just in this case, we just say, okay, we just say, okay, try, right? Try if F1 is this function. Function of Q, capital Q, right? So that is F1 type, and have this formula. M omega Q small over 2 whole times T. You may ask why you select this one. Yeah. If I have no experience, I do not know how to do that. But this is, you will see it works. So yeah, if you have more experience, you know this previous. Okay, so this Q here is dimensionless, right? Since in angle, that is angle. So that means we introduce or do this canonical transformation from the old one, which is general coordinate, is a displacement, but when we convert to new one, which is angle, we are going to do this one. That is the F1 type. Okay. So once we select this, then we are going to do the following is just try to make the canonical transformation, right? Use this. So now P here, right? This is only one, so we don't need the index. P equal to partial F1, partial Q, right? So now Q is here. 2 to cancel, so now M omega Q whole times T. That is P. I'm going to get the equation 1 here. And then the capital P here is negative partial F1, partial capital Q. So m omega q square over 2. Cotangent theta equal to how much? 1 over sine square, right? So that is 1 over sine square q. That is equal to 2. So the new canonical conjugate momentum here is a mixture of these two. Okay. So that is what W. Then now from here, you remember the reason why we use this, we are going to find this transformation equation. The relation between old and new, right? So now let's first from here, you see that this old one is function of new. So from here, now, from 2, equation 2. So we can find Q, right? We just move the Q to the left hand side and P to the right hand side. Q is square root, since it's square, right? And P go to P go to P here. We have a 2 factor 2P, factor P, and up. Then this one square. So this is just equal to itself, right? Now this is one of these transformation equation. The relation between old canonical variables and the new canonical variables. Okay. Second one. Then so the reason why you see here how to do that, you look at this equation. If there's only one old and the other are new, so you can immediately get this solution. Then this one, you see we have 2 old, 1 new, right? We need a new this relation. So what you have to use this substitute. So because we need P, right? So substitute 3, 2, 1. Then we immediately got P equal to m omega. Q is this one, right? Square root 2 factor P and omega sine of Q and then cotangent. Okay. So sine they cancel, right? So we have the cosine and this one goes inside 2 capital P. Capital P m omega since you can put inside here, and this is a cosine. See here, I have the relation old and new. So from this way, and that is why we use also. This help us to you remember your notes, right? All right, so now, once we have this, so the remaining part is, since I use F12, K, right? Now the next step is calculate the Hamiltonian. The K as a function of new canonical variable. Let me use T here, but you will see it does not depend on time. It's equal to H old P plus partial F1, partial T, right? This is a formula. So, I'm going to use here. So now let's see here. K new Hamiltonian is old one. Old is here. Okay. If I rewrite because I use omega, right? So I rewrite omega. Just take it out one very easily. Okay. So I rewrite this one equal to P squared plus m squared minus B plus B. You still can keep K, but it's, since we have omega here, so I want to consistent. All right, so now let's see so K here, right? So H is half of m P squared. P is here, equation 4. This is P, right? So that is P squared is 2 capital P m omega cosine square theta, right? This that. And plus m square omega square Q square. Q square is this one. So that is 2 capital P m omega sine square Q. Okay, so here this cancel, this is the same, right? 2, so now we have a 2 to cancel, cancel, so we have a P over P omega. Omega P, right? Omega P take outside, and then cosine square Q cosine square Q, this is 1. So that is omega P. See here. This is my new Hamiltonian. And yes, K equal, okay, so now you see K equal to omega P. Q is cyclic. In this case, right? After this canonical transformation. That is our goal. Okay. So once we have this, now we immediately know we can apply the equation, Hamilton's equation motion. So capital Q dot is partial K, partial capital P, right? And that is omega. Okay, if I say that is equation 5. 1, equation 5, then we have this. And then the capital P dot is negative partial K, partial Q, which is 0. So yes, capital P is constant. It makes sense since this capital Q is cyclic. So the corresponding conjugate momentum speed, okay, speed constant, right? So now we can solve from here. So dq dt equal to omega, then capital Q is omega P. And here P is constant, so now you can see P here. The relation between P is K over omega, right? From here, the relation 12. And K, what is K? Okay. It's an H, right? Because this is 0, partial F1, partial T. So K equal to H. Whatever its formation is different, but it is energy itself, so it supports this initial energy. Energy of system, and the momentum keep constant is conserved. Okay, so with this one, you see they solve this very easily. Now you back with this 6. Now, the last step, our goal to solve this one, right? P and Q. So we have to go back to substitute this into here and here. Find the final, right? So then the last one Q. Okay, let me say this. Sub and Q equation 6. Two equations. So we have equation 3 and equation 4, which are the transformation equation. So equation 3 is Q equal to square root 2 capital P n omega sine Q. Q is omega T. So that is and P is what? P is energy of omega, right? So 2 energy omega, so m omega square sine omega T. Yes. And then the P is here, right? So square root 2 P and omega cosine omega T. You can substitute P here, so you can see this is omega cancel that is 2E and cosine omega T. That is final. So this is a function of the trajectory of this canonical variables, a function of time, and that is dynamics, right? Now I can use this to give you some idea what is in the phase diagram, those variables. So now let's read the plot. Okay. Q in this case. So now if this is equation 7, and 8, right? From 7 give us Q as function time. So if Q as function time, that is sinusoidal, right? Sine. Yes, it is a sine. And but if capital Q as function time, you will see here capital Q is omega t. So that's linear, right? That is chemical Q. Then the lower conjugate momentum as function time as cosine, right? So that is something like this. But this capital P as a function time, it is constant. Right? That is energy over omega. So you see this, by canonical transformation, it can help us to solve this equation of motion. Then if a trajectory, so that is a function of Q and P. It's function of Q and P. You see this is nothing but this ellipse. But if in this new phase diagram, the relation between capital Q and capital P, because capital P does not depend on this capital Q, right? So this is only constant. Okay. The others. Let me brief summarize before we go to the new technique. Let me first summarize. With those examples, I hope you can understand the advantage of the canonical transformation and how to make the canonical transformation. So the goal is to make a summary. Transformation. First, what we need to find, find geometric function, right? Find this. And how to find this, this is a challenge. And that is why in the next step, next Tuesday, we are going to introduce another way. Because as we say, I introduce that one, we do not, you say why you select one like that type, right? That is right. But if we find this one, then you use this this one, different type, right? So depending on what kind of different type you can select. Then you're going to find this. Then you're going to, okay. Substitute df for this equation of canonical transformation. Which one is this? Q is without Pg minus h equal to summation capital Q naught Pg minus Q plus Pg. Now this, from here, then we can find the partial derivative of the geometric function, which gives us the set of the relation or bridge between the old canonical variables and new canonical variables, right? So then they find, after that you can find the partial derivative which is example, right? So example, if F1 type Pj is partial F1, partial Qj, and capital Pj is negative partial F1, partial capital Qj. So then this generating The goal is generating the transformation equation. Equations for the old one, Kg, Pg, and new one, capital Kg, capital Pg. That is Qg is a function of capital Pg, Qg, Pg, T, and Pg is a function of capital Pg, T. So that is okay, that is number 5. That is actually this one here. When you use this one, and then what the goal is, you need to convert. Remember, you need from here and make the convert to or inward to find this relation between old and new, and substitute to another one. So the goal is try to alter this, right? That is the number 4 step, number 5 step, and then 6. After that, Sanders Q. Okay, the Q as a function of capital Q, capital P, and the PG to H and partial F partial. So here, when I say Fi, it's depending on type. Which type, right? Type 1, type 2, type 3, all mixture. So the details here. When you do that, and the goal is obtain K, right? That is your goal. Once we have this, then we can have solve the Hamilton's equations of motion in new K or new phase space. That is, when you have a K, so you can solve this. And after that, Sanders Q is solutions. From here, right, solutions is the solution Qj as a function time, and Pg as a function time, to is the old one. That is the final. So that is our goal. And we want to solve this this old kinetic variable is very complicated, and then we are going to take the kinetical transformation to make this so this equation become simple. Then after we can solve this, we go back to number 5 again. Okay, I think let's stop here. And this is the first topic in chapter 9 that we introduced. Where we want to study the kinetical transformation, and how to do that, we need a generative function. And as I make this question here, it is challenge. So next, follow this topic is we are going to find this general approach to make sure that even though do not find this, if we know the relation between old and new one, we can use this so-called symplectic condition to prove this is a canonical transformation. I'm thinking if I assign the homework from chapter 9, let me think about it. We cannot wait until finish. not almost the end of this semester. So maybe assign 1 or 2, just like make some practice. I'm going to, yeah, maybe next Tuesday,
Okay.
yeah, do practice.
So for a 3D system, just like for the 2D system mixture form, for the 2D you have your F1 type and your F2 type. So for the 3D system, you would have.
It's up to you. But you want to have a mixture for particle 1, F1, particle 2, F2, particle 3, F3. This really arbitrary.
Yeah. Okay.
Yeah. So maybe all are F1, right? Like I gave this n particle, like J, just equal to summation of Qj and capital Qj. That is for n particle. So that is why here it is not easy for us. If we have very experience, then maybe we know how to build up that generating function. If not, we have to find another way. So, yeah. But this is a starting point. That is to give us an idea. And later we'll also set up the relation between the generating function and the new method which we introduce. Okay, great, great.
That's fine. You can leave. We'll erase it.
Okay, I think so. Okay, she was on. Sorry, I write quite quick, right? All right.